Everything good? Oh. Yeah.
Windows P or something?
Oh, maybe we need to function F7. Is that it?
Maybe
let's try
Windows P at the same time. You change.
This was another.
This is another Zoom call. Yeah, we did. Yeah. I think it. Well, I see. So there. It's not the. Maybe it's.
Yeah, I think it should be.
Okay. If you press do this and then P. Yeah. Bring up an option. No. Then you want to duplicate one of them.
Duplicate.
Hey,
All right.
awesome.
Okay.
Well,
bar at the bottom.
How do we remove this thing?
Maybe go full screen now. Perfect.
Oh,
Okay.
All right.
Good.
Great.
Okay, we'll begin now. So our next speaker is Isaac Kim, who will be talking about entropy scaling law and the quantum marginal problem.
Hello? Okay, so I'm going to tell you about the relationship between entropy scaling law and the quantum marginal problem. So for those of you who don't know what the quantum marginal problem is, I'll first start with the marginal problem. So if you take, let's say, probability course in your undergrad years, you probably asked to, you're probably given a like a probability distribution over, let's say, 3 random variables, X, Y, and Z, and you'll be asked to compute the marginal probability distributions, let's say by summing over the random variable Z. But here we are asking an opposite question. So what is given to you are the marginal probability distributions over, let's say, X, Y, Y, Z, and X, Z. And the problem that you want to answer is there a global probability distribution which is compatible with these marginal probability distributions? And if such a global probability distribution exists, we say that these marginals are consistent. And as you can imagine, you can imagine a very straightforward quantum version of this problem. This is known as the quantum marginal problem. And here, basically, you replace the marginal probability distributions to marginal density matrices. So for example, you're given density matrices over X, Y, Y, Z, and X, Z, and you want to decide if there is a global state, let's say over rho tilde X, Y, Z, which is compatible with this given data. Again, if such a global state exists, we say that these marginal density matrices are consistent. So you might be wondering, this is kind of a strange question, so why should one even care about this? Probably there are lots of motivations, but at least for me, the main motivation is quantum many-body physics. So oftentimes when you write down the Hamiltonian, you can write the Hamiltonian as a sum of locally interacting terms, each of which act on like a finite number of particles. So if you formally write down the expression for the ground state energy, on the first line, you have this optimization problem over an exponential large space, but then you realize that the Hamiltonian is a sum of local terms. So when it comes down to the expectation values, well, you can just use the marginal density matrices. So if you can somehow characterize the set of marginal density matrices, which are compatible with some global quantum state, it seems like you might be able to use this for performing some efficient calculation of ground state energy. It's a hope. So it doesn't quite work, but at least that's the hope at the outset. And this is because the problem deciding if these marginal density matrices are consistent with some global state or not is actually a hard problem. So formally, this problem is known as the consistency problem in quantum complexity theory. And an important point to notice is that this problem is actually QMR. So you should not really expect to have any classical or even like a quantum algorithms that solves this problem efficiently. So to make progress, you need to make some assumptions, and the assumption, and I'll tell you about one such assumption, which will allow us to make some progress. But I should note that there is one well-known solution to this problem for the case where the marginal density matrices have supports which do not overlap with each other. Then clearly, you can simply write down the global density matrix, which is a tensor product of the given marginal density matrices, and this is known as the mean-field solution. The nice thing about this is that the solution is trivial. You can check that it's correct, But the downside is that, of course, this is a bad approximation in many cases. So because you are in a product state, you have a fundamentally zero entanglement beyond a certain length scale. So it has a very limited entanglement structure, and it is fundamentally incompatible with certain physical systems that which we expect to exist in nature, such as a toric code or the phases of the toric code. So that said, there are some alternatives. Like in 1D, we have like good alternatives such as DMRG, and if you want something more rigorous, there's this very nice algorithm by Lando, Wittig, and Vazirani. And in 2D, there has been a lot of recent progress on understanding the entanglement structure of these systems, like we just heard, and also developing new algorithms based on the tensor networks. But I think it's fair to say that right now, there is no single algorithm like DMRG, which solves all the problems in 2D. And my point of view is that before that day comes, we should keep thinking about the entanglement structure of these systems and ways to exploit that to solve these problems efficiently. Okay, so with that, I'd like to report a non-trivial solution to the quantum marginal problem, which I think is relevant for 2D quantum systems. To be clear, this is a solution that holds true even when the marginals do overlap. So it's in that sense, that's a non-trivial solution. So the physical setup is that you have a locally interacting, let's say, quantum spin system on a 2D lattice. And we anticipate the Hamiltonian that describes the systems to be a sum of local terms, each of which are supported on some constant size ball on this 2D lattice. So naturally, we demand the density matrices to be supported on these constant size balls on this 2D lattice. And at the high level, the main statement looks like the following. There are some conditions. The first condition is trivial, so I'll just tell you. The first condition is the density matrix should be locally consistent with each other. For instance, if you look at these circles, each of these circles are supposed to represent the supports of the individual density matrices. So you see this yellow one, and you see this red one, and they overlap on some region. So if you take the reduced density matrix on this overlapping region, these local density matrix should give you the same result. If you think about it, if this condition is not satisfied, clearly there is no global state whatsoever that is consistent with this data. So this is also a necessary condition, also the minimal condition that you need. So it's really the second condition, which I'll explain in more detail later, that really lets us say something non-trivial. And the informal statement is that if these conditions, whatever they are satisfied, then these density matrices are consistent with some global state. So before I tell you about the condition, let me first tell you about the implications behind this. It basically says that for any state that satisfies our conditions, you can compute the expectation values of observables supported in constant size balls in constant time, because what is given to you are the reduced density matrices, and that defines the global state. And a little bonus, which I won't have much time to talk about today, is that you can actually compute the maximum global entropy consistent with the density matrices. This is like a pretty non-trivial statement. So what this means is that practically speaking, we have a class of many-body quantum states that allows an efficient calculation of classical calculation of energy and free energy. So it'll be interesting to see how practical this approach will work in the future. That said, we have 3 questions that I want to address in this talk. One is, what exactly is this condition? What is this mysterious condition? And the second thing is, this condition, you might be wondering, maybe it's too strong. So maybe it's only applies to a very select set of states. For example, maybe it secretly implies that there is a global state, but maybe that global state is a tensor product state, which would be kind of boring. So I'll address that issue. And the last thing is, what exactly is the structure that allows us to prove this main statement? Because that's clearly a non-trivial statement. So there's something non-trivial going on. Okay, so let me start with the first one. So the setup, as I said before, is a 2D quantum many-body spin systems. Imagine you have a locally interacting quantum spin systems. Each of these black dots are like some finite dimensional qubits. And what you do is that you first coarse grain the system. This is simply to state the result. Like so far, I'm not doing anything fancy. I'm simply regrouping some of these so that I have this triangular lattice, which will make my life easier in explaining the main result. So in that coarse grain system, the statement looks like the following. So I see there are lots of diagrams, which would be probably hard to parse, but let me first say that the first condition is the following. So we assume that the marginal density matrices are given on this like a 3x3 size little clusters. So that's our fundamental data. And as I told you before, we demand them to be at least locally consistent with each other, because that's the bare minimum condition that needs to be satisfied. So what are these mysterious conditions 2 and 3? So first of all, S means that it's the von Neumann entropy. So that means whatever is in the parenthesis is a density matrix. So what does this diagram mean? So we have a 3x3 cluster. So we have a reduced density matrix on that cluster. And what I'm doing here is that if you see a gray square, what I'm taking a partial trace on that particular subsystem. So here you start with a density matrix on a 4-pi type density matrix, and you're taking a partial trace on this gray square. So what remains is a tripartite density matrix over these 3 squares, okay? So you have some conditions, which admittedly looks complicated, but what I'm hoping to convey to you in this slide is that these conditions are truly something that you can verify directly from the reduced density matrices, because calculation of the von Neumann entropy for finite dimensional matrices, you can just run it on the computer. So if these conditions are satisfied everywhere, then one can show that there is a global state that is consistent with all the marginals. Okay, so the second question, to which systems does this solution actually apply? So this is the part which is more heuristic. The key statements of this work was already stated in 2 slides ago. And here I would like to justify the physical relevance of the solution. So ideally, we like to argue that the constraints that we propose are general enough that they include a large class of quantum many-body systems so that we can apply this to a variety of systems. And if one asks, like, can we really say that? I would argue that the answer is yes, because these constraints are satisfied if the underlying state satisfies what is known as the entropy scaling law. It essentially states that the entanglement entropy of a subsystem can be expressed as a sum of term that scales like a volume of the underlying system plus a area term plus some correction and et cetera and et cetera. So if you're a physicist, like a condensed matter physicist, you would think that this condition is kind of reasonable. If you're a computer scientist, you would think that this is like a very, very strong assumption. And I agree that it's a strong assumption, but the important point is that people have actually studied the scaling law for a variety of systems in exactly solved models using quantum Monte Carlo and also using DMRG. And it seems to be that this condition holds for quite a lot of systems. That said, there are counterexamples for which this is just directly violated. I can tell you more about it, but for now, I will just say that we have a way to get around this problem. Okay, so the last one. So how do we actually prove the consistency? In a way, this is really trying to address like what is the secret sauce behind this work? And the key concept behind this is what is known as the quantum Markov chain. So this is a concept that appears in quantum information theory quite frequently, a very important one. And the definition is the following. Suppose you have a tripartite quantum state. We can define its conditional mutual information as a certain linear combination of its entanglement entropies. And we say a state is a quantum Markov chain if the conditional mutual information is exactly equal to 0. That's just a definition. And what's nice about the quantum Markov chain is that it admits the existence of a recovery channel. So for instance, if you remove one of the subsystems, let's say C, by taking a partial trace, then we can show that there exists a channel acting purely on B that recovers the original state, rho ABC. Okay. And another nice thing about the quantum Markov chain, which I think is something, it's based on a very nice observation by Kotaro Kato and his collaborator, is that if you're given 2 quantum Markov chains, there's a sense in which you can merge them together to form a larger Markov chain. So if you look at this statement, the statement says that if you have 2 density matrices over ABC and sigma BCD, such that they're both Markov chains, and if they are locally consistent with each other, then there exists a density matrix tau ABCD over the global system, such that this tau is consistent with rho and sigma, and at the same time, it's again some Markov chain. The key point here is that, first of all, we infer the existence of a state on this global system simply by inspecting the conditions on ABC and BCD, okay? So that's a nice thing. That is the spirit of what we're trying to do. The second remark is that tau is again a Markov chain. So this is like a little diagram that I wrote down. You have like 2 small Markov chains and you combine them together to form a larger Markov chain. So you can sort of imagine like bootstrapping this argument to start off with like little Markov chains, and you combine them together to form a larger quantum many-body state. essentially at the high level, that's what's going on. So I won't have much time to talk about the details about the proof, but I just want to show you some pictures on how I think about this. So the lemma that I showed in the previous slide can be thought of as the following. So you have these two Markov chains that satisfy these condition mutual information being equal to 0 condition, and you can somehow combine them to get this 4-partite state. And you can probably imagine that if you have like a sequence of like quantum Markov chains, like here, and that is arranged on a single line, you can imagine like merging them all together to form a one-dimensional quantum many-body state. And in 2D, you're doing something similar, except something is a bit more complicated. So suppose hypothetically, you know that you're given, suppose you know that there exists some state on this slab-like region so that you obey the Markov chain condition over these subsystems A, B, and C. And imagine you have this similar density matrices like translated along the Y direction. Then you can sort of imagine the 1D argument would still apply. The non-trivial part is in showing that the existence of this slab-like region, which obeys this condition, follows from our local constraints. So that's really the main piece of work is going on in this work. Okay, so I'd like to make a little comment on the perspective that I have on this problem. So I think understanding the entanglement structure of these 2D systems is very important. So it's very important to understand if we know the area law, but there is this lingering question. So once we have area law, like, is that going to be the end of the story? Unfortunately, it doesn't seem to be quite that, because simply having an upper bound on the entanglement does not necessarily imply that you would have like efficient classical description. That said, maybe the mathematics that allows us to prove area law may allow us to go jump directly from gap to the efficient classical description. And here we're trying to do something similar, but slightly different. So what we're trying to do is starting from gap to this entropy scaling law, which will be probably significantly harder. But if you assume that's true, then you get a little bonus that you get an efficient classical description for free. So that's what I think about this work. Okay, so the conclusion is that we have a non-trivial solution to the many-body quantum marginal problem, which is applicable to 2D systems, which directly leads to a new variational approach to approximate energy or free energy of these quantum many-body systems. And an interesting problem would be to understand whether you can extend this to a larger class of systems, approximation guarantee, and also the robustness analysis. Okay, thank you.
Questions?
Hi, Isaac. Thanks for the wonderful talk. I didn't understand, is this maybe constructive in the sense that you get a sequence of channels?
Yeah,
do the
good question. This is actually constructive. So in principle, you don't need to actually construct the global state, but in this case, it's constructive.
It's constructive in the sense that you get a sequence of channels.
Right. So in fact, I get a PEPO of some sort.
Okay.
Yeah.
Thanks.
Hi, Isaac. Thanks for the talk. So am I correct in understanding that when you had the diagrams on the 14th slide, those are sort of mutual information conditions, like on 2 and 3 side structures?
This 4-partite state, maybe it's better to just look at this.
No, you had the constraints with the entropy of these 2 by 2. Those are like mutual information constraints.
Those are like condition mutual information conditions. Yeah. So the second condition that's is the condition mutual information condition. The last one, insofar as the second condition holds true, is a conditional mutual information condition. But essentially, everything is conditional mutual information condition.
And another question, if you're sort of stitching the Markov chains in some sort of zigzag pattern, how does this scale if you're given some noisy density matrices,
right?
Local density matrices?
Yeah, so this is an open problem at this point. That said, we expect this robust version of quantum Markov chains would probably lead to similar result, but this needs to be worked out.
So is this lemma
robust?
Oh, okay. So this, I don't know if there's like, this is like written down anywhere, but it's certainly true. There's a robust version of this lemma. Yeah.
I have a question about the last slide about the open concept. So what's the difference between the second point and the third point? So approximation and robustness.
So approximation guarantee, maybe I should have been more specific, saying something that 2D gap systems can be described by this with some certain like 1 over poly n error or something like that. That's what I had in mind. Whereas the third one is when these constraints are not satisfied exactly, then what would happen?
What's the second one again?
Second one is like, let's say for 2D gap systems show that you can approximate the local properties up to some error epsilon using like a certain size reduced density matrices. Yeah.
Thanks for a great talk. So tensor networks provide an efficient parameterization of many-body states. Is there a way of finding an efficient parameterization of the states which satisfy the conditions that you described?
Well, in a way, this actually gives you a tensor network. It's just that we end up not using it unless you're interested in like a long-range 2-point correlation function. So this would be one way, but there's also like interesting work like isometric tensor networks, which is actually efficiently contractible. So maybe that would be one way.
But maybe I can ask the question a different way. So how do I get? So I could propose a bunch of density matrices, and then I would have to check that they satisfy the compatibility condition. I'm saying, is there a way of proposing them so that I know that they satisfy these conditions, which is not obvious a priori?
Well,
or I can ask you.
Yeah. Okay. Yeah. Maybe we can talk about it later. Yeah.
So, do you know anything about the uniqueness problem, or for instance, if you know there is a pure state that is compatible, will you find this pure state, or will you find another one which is compatible with that?
So I actually don't know if it's a pure state. In general, it'll be a mixed state actually, because I'm simply essentially what I'm doing is that I'm reconstructing the maximum entropy state compatible with this local data. So yeah, there are probably other states that's locally consistent as well.
Thank you.
I think I had the same question. So it's about the purity, right?
Hi, great talk. Thank you. That's also my question. But another question I had was, if you don't have the density matrices, you just have some local measurements. Can this be extended to that?
So if it's rich enough that it reproduces the density matrix, then yes. But otherwise, I'm not sure. It's a hard problem.
Okay. Let's thank Isaac again. Okay, the program continues in the main ballroom.
Yeah, that's right. Hey, you talked about approximation.
Great talk.
I didn't know how to handle the much.